Hey there, and welcome to part 3 on a series of videos I'm making on limits and continuity. So far we've discussed the definition of continuity and how we define continuity for a function. We've looked at some properties of continuity and how to tell when something is going to be continuous along an interval and the different types of discontinuities that we could encounter. So here, what you're seeing on this page are very similar to properties of limits that you've seen. The scalar multiplication, the summer difference, the product quotient, and the composition rules that we see for continuity are really the same thing that you've seen for limits. So there's really nothing new to talk about here. Here is the definition of continuity again, in case you missed it in the first video, that f of c must be defined. The general limit of the function as x approaches c must exist, and those two values, the limit of that function as x approaches c and f of c, have to equal the same number. So here we're going to be taking a look at a piecewise function, and we're going to evaluate it for 3 different values of c, a -3, a +3, and a +7. And what we're being asked to do is it's very similar to the table that you saw in the beginning of the first video. We're going to just say, okay, well, what is the function as we evaluate it for that value, for that number? Do the left and right, what are the left and right hand limits? That will tell me what the general limit is. And with that information, I will be able to tell if there is continuity at that point or not. Now, you should be able to look at the graph and tell whether there's going to be continuity or not. So looking at c of -3, you can see that we have a hole there at -3. So right away you should be able to say, well, it's not going to be continuous. But let's use the definition of why it's not continuous there. So looking at c of -3, the output of c of -3 is going to be a 2. Well, that's one thing that we need to evaluate. The left-hand limit and the right-hand limit do approach -1, so the general limit does exist, and the general limit is going to be at -1. And I feel it, there we go. But f of -3 is equal to a +2. So according to the definition, it cannot be continuous because the general limit does not equal the defined function amount. So now we're going to try to evaluate it for c of 3 or x of 3, however you want to think of it. And you can see there, well, looking at the graph, we have a vertical asymptote, it looks like. Well, how do we actually use the definition to show why it's not continuous? So evaluating the function for c of 3, the left-hand limit and the right-hand limit both go to infinity. However, as we've discussed in previous lessons, the limit does not exist at an unbounded region. So the general limit does not exist at the vertical asymptote. Now we can still evaluate it. F of 3 will be undefined. I could not plug an x number in there and get an answer out. So here I'm going to say it's not going to be continuous because according to the definition, the limit as x approaches 3 does not equal the f of 3. But you could have given probably other explanations about why it's not going to be continuous. There's a vertical asymptote there. F of 3 is undefined. The general limit doesn't exist. All of those would probably be good candidates for why you could say that that function is not continuous at that point. So now we're going to be looking at it at f of 7, where we have our jump discontinuity. So again, we should be able to understand that these are not going to be continuous. But let's see how we would use the definition to show that it's not going to be continuous. So the left-hand limit and the right-hand limit, first of all, they don't match. So because the left-hand limit and the right-hand limit don't match, the general limit doesn't exist. That in and of itself can quantify or be used for justification why the function is not going to be continuous. F of 7 is defined at 6, but again, the general limit being not existent and the f of 7 giving us a 6 for our output, those are definitely not the same, so it violates the definition of continuity, so no, the function is not going to be continuous. Now what we want to be able to take a look at is determine whether or not a function is going to be continuous without having a graph? How can we evaluate these particular functions to see if there's going to be continuity or not? Now I'm going to be upfront and say that these are going to take a little bit more work than you may be used to for some of your limit things, because in order to show that a function is going to be continuous or not, there's those three parts that we have to have. We have to have the general limit that exists. We have to have the defined function at a point, and those two values have to be the same. So here we're going to be evaluating f of x is equal to 1 over x minus 3. Now I'm going to look at the left-hand limit. The left-hand limit is going to show me that I would approach a negative infinity. The right-hand limit would show me I would approach a positive infinity. So since the left and the right-hand limits don't match, the general limit simply does not exist. I can try to evaluate the function for f of 3 and show that that is undefined, which makes sense because if you were to graph it, that's where the vertical asymptote would be. So here, this, according to the definition, cannot be continuous at x is equal to 3 because, first of all, the limit doesn't exist. You could also say that, like we saw in the last three examples, that the defined part and the general limit don't equal each other, something along those lines. So let's take a look at example B. Here in example B, we have a rational function, and looking at the denominator, I really want to evaluate this as x approaches a negative 2 because that's what is going to give me something that is undefined or something that is 0 in the denominator. So with most other rational functions, we definitely want to try and simplify it. And when we factor the numerator, we see it is going to simplify to just be g of x is equal to 2x plus 3. So now again, I want to look at the limits. What's the left-hand limit? What's the right-hand limit? And we see, hey, look, the left and right-hand limits match, so there is going to be a general limit for this function as x approaches negative 2. We will get a general limit of negative 1. Well, moving on from there, when we evaluate it for 2, unfortunately, it's not going to be defined at that point. Therefore, g of x is not going to be continuous at that point of negative 2 because the general limit does not equal the defined value of the function, which is unfortunately undefined. And again, you should be able to recognize that we're going to have a hole in this particular function. And I think I have the coordinates off. I think I have the sign on my hole coordinates wrong. I think it should be a 2 and a negative 1. But either way, there's definitely going to be a hole in the function, so it's not going to be continuous there. Now, these next examples are going to take a little bit of work also. So please make sure that you have the time to work through them and you have adequate space to work through them before continuing the video at this point. I don't want to stop it here because I know we're getting long on time, but let's just go ahead and try working through these things here. Use the definition of continuity to find the value of k that the function will be continuous for all real numbers. So here we have these two piecewise functions, and we want to make sure that they would be continuous at their point where their domains are restricted. Sorry, it took me a second to get that out there. So there's a process that we're going to use for these functions. Let's look at example A first. G of x is equal to k times x squared along the interval where x is less than or equal to a positive 2. And we have k times x, I should say, minus 6 on the interval where x is greater than 2. So first of all, I want to see what am I going to get if I evaluate both of these pieces for 2? Well, substituting the 2 from the left-hand side or the right-hand side into the function, the left-hand side will go to the top part of the function, the right-hand limit will go to the bottom part of the function, so that's why I'm substituting the 2 into those two pieces respectively. Now so here I'm going to take what I have there, the left-hand limit and the right-hand limit, and I'm going to set those two equal to each other, and I'm going to treat it like almost like a normal equation. So the left-hand limit, when I simplify it, that's just going to be 4k because 2 squared is 4. And the right-hand limit is 2k minus 6. So when I solve for k in this case, I get k to equal a negative 3. So now I can take that negative 3 and I can evaluate it. I can plug it back into those functions and show that in both cases I get a negative 12. So the left-hand limit and the right-hand limit match. That means at negative 12, that means the general limit would have to be a negative 12 here. So this particular function, I would say, g of x, as x approaches a 2, the limit will equal a negative 12 and will be continuous at x is equal to 2, where our domain is restricted for our two pieces, as long as k is equal to a negative 3. Now, if you're feeling adventurous, you can go ahead and try to pause the video and work out example B on your own, but I'm going to go ahead and continue working here. Now, this one, the domain restrictions are at a positive 4, so that's what we're going to evaluate the limit at, and that's where we're going to see, well, what do we have? So very similar to what I did on the last example, I'm going to take the left-hand limit, which would go to the top part of our piecewise. I'm going to evaluate it, and so that's going to approach a negative 1 when I simplify everything there. I'm going to look at the limit from the right-hand side and substitute, the 4 in for the x there, and I'm going to wind up with the expression of 5k minus 16. So just like I did in the first example for A, at this point I'm going to take the left and right hand limits and set them equal to each other to see what would my general limit be at that point. So when I solve for k at that point, I get k is equal to a 3. Now I can go back and try to evaluate the function, and I forgot the as x approaches to part on my text here, so I apologize for that. But the limit of function h of x as x approaches a 4 should equal a negative 1 and will be continuous at x is equal to 4 when k is equal to 3. And that is it for that one. So here we're about 12 minutes. I'm going to go ahead and stop this part here. I understand that there is probably some hairy mathematics going on, so if you have any questions, by all means, let me know. I'll be happy to try and get those questions sorted out for you. But until then, guys, thanks for watching and take care.